All right, and then for real this time, Binaz is going to give us a talk on analyzing wide area network degradation. She's a principal researcher at Microsoft Research.
Thank you. Let's see if this works. Yeah, it does. Okay, hello everybody. I'm Binaz from Microsoft Research. I'll be talking to you today about our work on RAHA, an analyzer for wide area networks. The motivation behind RAHA was an incident that happened in Microsoft's wide area network earlier in the year, where essentially in our Africa region, we had multiple fiber cuts, which caused Africa to lose capacity to the rest of the world, and many of our services in that region got impacted. The question we asked was, after the first failure happens, can we analyze this network, raise an alert for operators to know the network is at risk, and then once we have that alert, find a way to mitigate that problem? The problem is, though, before the failure happens, there's many possibilities of where the impact might be, which links might fail, and what demands would cause that failure. And I'm going to give you a little bit of a spoiler ahead of time. We actually ran RAHA in this scenario, and it found the exact link failure that caused the outage at the time. Okay, so what does RAHA actually do? When a failure happens, we take the topology after the failure, the set of paths that are available, and the link failure probabilities in this topology based on past events that have happened, feed them into RAHA, and RAHA generates an alert if the network is at risk. Now, the thing is, as part of RAHA, we also have mechanisms that help operators figure out where and how to add capacity. When these alerts happen, because we don't have time, I'm not going to go into the detail of those mechanisms, but if you're interested, please read the paper or find me outside, and we can talk about those. Okay. So naturally, when we're talking about a system like this, we need to first answer one critical question, which is, what are the things that influence how much the network is at risk of failures? Well, part of this is the difference between a healthy network and the network under failure. And this is the key thing that most prior work missed in this space. Everybody looks at what's the most impact on the network when failures happen in isolation without actually considering the initial design point the network had. But we designed the networks to be resilient to failures. There's multiple papers that we at Microsoft have published, Meta has published, Google has published, on how we do that. And so we need to consider what are the scenarios that actually degrade the network compared to this initial design point. So I know this is a little bit of an unintuitive point, so let me go through an example to show you exactly what I mean by this. So I have a very toy topology here. And this topology has capacities on each edge, as we networking people are used to seeing. And I have two specific demands. One wants to go from node B to D, and it has two paths available to it, one directly from B to D, and one that goes through node A. And a symmetric demand that goes from C to D, and it has, again, two paths available to it. Now, based on past history of traffic, let's say we're going to limit these demands to be between 6 and 18 for the demand between B and D, and between 5 and 15 for the demand between C and D. Okay? Let's say my objective is I want to route the most amount of traffic in this network. So obviously, when I want to look at the worst case impact, I want to find scenarios that cause a network to route the least amount of traffic, right? So what's the first obvious thing I can do? Well, I pick the lower end of the demands. If I have less demands, I'm going to be routing less. And that's what most prior work actually do, because they look at what's the worst case impact in isolation. And in this case, I'm going to pick demand between BD to B6, between CD to B5. Very simple. And then I'm going to look for the worst case failure that impacts this. Well, let's look at first what a healthy network would do in this case. A healthy network would send 6 amount of traffic on that link between B and D. And it would send 4 from C to A to D, and 1 from C to D. Okay? The worst case impact on this network under one failure is going to route 10 units of traffic by failing that link between C and D. So how much has the network actually degraded? By 1 unit. So now let's run RAHA on this exact same topology. It can pick any demand in that range and can pick a single link failure. So what it's going to pick is actually a demand between BD that's 13. Notice how it's on neither end of the spectrum, and CD 12. And if I route this traffic, and I'll ask you to trust me on this, the network without failure routes 25 units, and the network under failure, and RAHA picks that shared link that has 10 units of capacity is going to run out 16 units. So I've now degraded the network by 9 units, whereas the baseline was only finding a degradation that was 1. So that's the first thing that matters when we're considering failures. But I kind of snuck in one important point, which is variations in demand also matter. So let's assume when I'm solving this problem, I look at the average demand that I've seen in my network. So if I look at the average demand, and I consider degradation, so again, remember, this is how my network's performance is going to compare to the network without failures, I get that point that you see there on the corner. Now let me allow this demand to vary by a range. So that range is defined on the x-axis by a slack value. So how much factor of the average am I allowing to increase? And let me set the demand to the maximum value I can take in that range. I'm going to extend that red dot so you can compare. Obviously, the demand is going to increase just because the impact is going to increase just because I now have more demand to route. But here's an intuitive point. Look at what RAHA finds. RAHA, when you look at any demand that's in that range, causes worse degradation compared to either of those two scenarios. So the worst case degradation doesn't necessarily compare to the maximum, right? You can cleverly pick what demands you actually pick for the risk on the network. OK. Next thing that matters, and I think this is obvious to most of you, is that failure probabilities matter. When you look at prior work in this space, most of them consider up to k failures. But there might be a probable scenario that involves k+1 link failing that can cause a worst case impact on your network. And this is exactly what happened in the incident we had in Africa. We were considering up to 3 link failures, and the 4th one was the one that really caused the worst case impact. OK. And then last of all, and this I think is intuitive to most of you as well, is we obviously want to consider the objective functions that matter to operators. So in this case, it's the total flow that we route through our network, but we also sometimes care about maximum link utilization or other metrics. OK, so RAHA allows you to consider all of these things, and most crucially, it allows you to compare the healthy network versus a network under failure. Now let's compare this to prior work. So one of the prior work that considers risk is TEVR. It's a traffic engineering solution that tries to minimize the risk your network is under. And the only thing it is able to consider out of the 4 things that we care about is that it considers all failure scenarios. There's QARC, but again, it fails to compare the network with its healthy state. There's also U that was presented in the same conference last year that considers up to k failures, but it fails on all the other dimensions. What RAHA allows you to do is to consider all of these different aspects. OK, so how do we actually solve this problem? The intuition for this is actually modeling this problem as a game. So the game we're solving is we have an adversary that tries to maximize the difference between the healthy network and the network under failure. And it dictates the inputs to the healthy network, which is the demands, and to the network under failure, where here the inputs are going to be the demands and the links that it's trying to fail. And its objective is to maximize that difference. And so these two then compute their objective and dictate what the adversary gets. So by solving this game, we are able to answer the question that RAHA answers. So the question is, how do I actually solve this game? So at Microsoft, we built a tool we call MetaOpt that allows us to actually do this. We initially designed MetaOpt to be able to compare heuristics with their optimal algorithms that people use. So it took as input a model of a heuristic and a model of an optimal problem, and it would produce adversarial inputs that cause the heuristic to underperform and causes the worst case impact on that heuristic. So the intuition here, though, is that when I think of a healthy network, it's kind of like an optimal algorithm, right? The healthy network is the optimal state of a network. When I think of a failed network, in a way, I can think of it as a heuristic. So MetaOpt essentially applies, and I can use the adversarial generators to solve the same problem. And by solving the game that MetaOpt solves, I'm able to answer the question RAHA wants to answer. So what does MetaOpt actually do to solve this game? It models a problem as a bi-level optimization, where we have an objective which maximizes the difference between the optimal and the heuristic. And it has the optimal as an optimization problem and the heuristic as either an optimization problem or a feasibility problem. Now, have I solved the whole thing and I don't have any challenges to address? No, because what MetaOpt requires is that these inner problems, which are essentially the optimal state of the network and the network under failure, the network under failure, we have to model it as a convex problem because we have an objective here. So the problem is, though, if I think of a failure, it's kind of by nature non-convex, right? Because I have a binary variable at the very least, which is this link up or not? And so what do I do with this? Well, we got lucky in one respect, though. So when I think of what MetaOpt can do, the outer problem that we have can handle non-convexities. It's the inner problem that requires that we have entirely a convex problem. And so if I think of this inner problem, it views all of the variables in the outer optimization as constants. And so all I need to do is I need to figure out how to take these non-convex part of my model and move them into the outer optimization problem that I need to solve. And the way I do that, I'm going to show that to you in an example. So think of this, a very, very simple case where I want to just know what the link capacity is if the link fails. I model it as a constraint like this in the optimization problem, where I just multiply the constant capacity of the link by that binary variable we talked about, and equals to a variable that's capacity. The trick, though, is this variable that you see here is a variable in the outer problem, and the inner problem is considering it as constant. And because of that, I'm dealing with a convex problem when I'm solving this optimization. OK, so I know that was a lot of math. So let's go back to intuition. So what RAHA allows you to do is that it allows you to solve for problems that tell you how much risk is the network under at any given point in time. And it allows you to go beyond that, though. It allows you to also specify other constraints that you might care about. One of the things it allows you to do is to consider probable failures. But also, it allows you to enforce other constraints. One of the constraints, for example, Azure operators cared about was we want to enforce a strongly connected network. We don't care about those failures that cause like bipartite graphs. And we can enforce that as part of the optimization. We also allow you to consider different failover policies. So for example, one of the failover policies might be that you might route traffic on backup paths if you have one of your paths fail. And MetaOpt and RAHA on top of that allow you to actually support those types of constraints. So let me show you some results now. So remember, the key related work was due that was published last year in SIGCOMM'. We extended that a little bit by allowing it to also consider failure probabilities. And so we're looking at single failures that are more than X% likely. So that's the x-axis that you see here. And the y-axis is, again, degradation. Degradation being how much does a network degrade compared to its healthy state. Now, with 2 failures, obviously that increases. 3 failures, it increases a little bit more. But when I allow RAHA to explore the range of possible failures, it can find scenarios that are much more impactful. What if I look at tools that only allow me to look at a constant demand, so don't consider demand variations? Well, you see again that we don't really find the scenarios that cause a true risk on the network. Demand variations themselves are an important part of the problem that we're solving. OK, so with that, RAHA is built on top of a tool we built at Microsoft called MetaOpt. MetaOpt has had impact in a variety of domains. We've used it to consider and analyze machine learning models. We've used it to prove a tighter bound for vector bin packing than what theoreticians had been able to prove for the last 30 years. We have multiple collaborations with the product teams at Microsoft. And it's an open source tool that I would highly encourage you to play with and try. And if you have any feedback, you can reach out to either me at Microsoft, Siva, who's here in the audience, or Puriya, all of which us will be happy to answer your questions.
All right, any questions for Benaz? It's a talk before lunch. It's always, there's one.
At a high level, wanted to ask you the main question. Sorry, I think I wanted to, in general, ask you why should operators care about the main RAHA's objective, which is to find this difference between a healthy state versus a failover network, instead of the worst case scenarios that prior work has, always considered.
Well, so if you listen to the example that I was giving, the challenge is that worst case failures you talk about is not something that in practice is going to impact the network with the objective that operators care about. The degradation is actually the true factor, so the scenarios that you end up finding with that different objective are the things that actually cause an incident like the one we talked about in production. And the reason for that is the design point of the network is to consider scenarios that are common in practice, that can happen. And so if you do the thing that you were mentioning, which is you completely ignore that design point, you find scenarios that are interesting, but they're very unlikely to actually happen in practice.
Hey, Sanjay from Purdue, very nice work and talk. I wonder if you can comment on how easy it is to get probabilities of failures in the real world. I get very mixed feedback from operators on this.
Very good question. So we have historical data. So there's the nice thing, by the way, about RAHA is that you can completely disable that probability consideration in case you don't have that information available to you, and it works vanilla without those. The way we got the probabilities is we have the historical data in Azure for links that have failed in the past, and we use renewal reward theory to compute those probabilities, and that's relatively straightforward. Now, there is a question about how often do black swans happen. The tail end of that probability, right, is also interesting, and it's hard to estimate because you need data to be able to estimate those probabilities, and that's a statistical challenge that I don't think is, I think, something for theoreticians, not really practitioners, really to answer.
All right.